Gas. Gas is everywhere. It's in the air, in soda, in your body. It's in everything. The good news about gases is that they are easy to calculate, both theoretically and mathematically. What makes them easy to calculate are what we call gas laws. There are 5 of them. Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law, and the ideal gas law. Now, there are many examples of these laws, but I think a perfect example would be the Hindenburg. The LZ-129 Hindenburg was a German commercial passenger-carrying airship, the lead in its class and the largest by envelope volume. It first flew in March of 1936 before bursting into flames 14 months later on May 6, 1937, while trying to land in New Jersey. Now, this accident could have been a whole story itself, but how does this catastrophe relate to the 5 gas laws? But first, let's talk about how this 100-ton Goliath of an airship stayed in the air. The airship stays afloat using ballast filled with lighter-than-air gases. These gases provide enough lift to keep it in the air. The original design for the Zeppelin was supposed to use helium, a safe, non-combustible gas. However, due to U.S. export regulations on helium, they were forced to use the highly flammable gas, hydrogen. Now that we understand how the Hindenburg stays in the air in the first place, let's talk about how each of the gas laws plays into this. First up, Boyle's law. As the airship ascends, the outside pressure decreases, and according to Boyle's law, pressure and volume are inversely related, meaning as the pressure decreases, the volume increases. Because of this, the ballasts are never filled to 100% to allow room for expansion as they go up into the air. Next up is Charles's law. Charles's law states that as temperature increases, volume will also increase. As the volume of the gas increases, it will become less dense and provide more lift. However, if the gas got too hot, engineers would need to valve the gas to release pressure and prevent the ballast from overexpanding. Third is Gay-Lussac's law. This law states that in a fixed volume container, as temperature increases, pressure will increase. This expands on the 2 previous laws because if the ballast is filled to 100% and cannot expand anymore, the internal pressure will cause the ballast to burst. Avogadro's law is the reason why the airship can stay buoyant. While the air in our atmosphere has a molar mass of about 29 grams, hydrogen only has a molar mass of about 2. This means that the hydrogen gas is significantly lighter than the air it displaces and generates lift. The ideal gas law is the big picture for flight physics. PV equals nRT. I'll put all the variables mean on the screen, feel free to pause and read them. Maintaining a constant altitude means a constant pressure and volume. To maintain the specific altitude, engineers had to balance the amount of gas N with the ambient temperature, T. Now, this information is cool and all, but none of it actually relates to how the fire started. There are many theories as to what exactly happened, but the most likely theory is that one of the ballasts began to leak the hydrogen gas. Now, this makes sense until you think about how the gas ignited in the first place. Prior to landing, the Hindenburg had just flown through a storm. It's theorized that this storm statically charged the fabric of the Zeppelin, similar to how you get shocked when you touch a door handle after walking on carpet. This tiny spark of static electricity is believed to be the cause of the ignition. From there, the fire spread to the fabric, and soon the entire structure was engulfed in flames. The news coverage on this event greatly diminished the public's view on Zeppelins, and they were discontinued shortly after when international passenger air travel, aka passenger airlines, became popular. It's a shame these big Zeppelins aren't still around today. Though much slower than airplanes, they provided luxury travel for hundreds of people at once. The whole disaster would have been prevented if the US had lifted the export ban on helium. And who knows, maybe they would still be used to this day.